بسم الله الرحمن الرحیم الله بالله و نعم المولى و نعم النصير. Last time we talked about dynamic formulation using Lagrange approach. Today we will rewind again dynamic properties, formulation properties of the system. As we mentioned, for any serial manipulator, the dynamic equation can be written in the form of mq double dot, the mass matrix, plus vq dot, the Coriolis and the centrifugal vector, and gq, the gravity-based vector for the system, is equal to q. Q is the actuated force or actuated force minus the friction forces that are applying to the system. Starting with the mass matrix properties, we would like to talk about these three parameters and see what are the different effective properties of these vectors and matrices. The mass matrix is like a similar mass, is a generalization of single body mass. We can show that as the single body mass is always positive, mass matrix is also always positive definite, like a positive definite matrix. And this can be found very easily because we define the mass matrix from the kinetic energy. And kinetic energy is always positive. And since the mass matrix is a quadratic form, the kinetic energy comes from the quadratic form of the mass matrix times q dot, and k is always positive. Therefore, the mass matrix is always positive definite. And this is very, very important, as we see in the next slide, for computer simulation, that this matrix should be positive definite. What does it mean? If this is positive definite for any configuration, this is a mass matrix is a parameter of q, and by moving the platform, by moving the robot, the mass matrix is changing. But this property never changes, and we have always positive definite matrix here. If this is positive definite, we can always inverse it, and this matrix is invertible. And we use the inverse of mass matrix many, many times in the simulation studies and in control. Furthermore, we can say that if this is a mass matrix is a positive definite matrix, it has a lower and upper bound. The lower and upper bound can be defined by the minimum eigenvalue and the maximum eigenvalue of the mass matrix in the whole workspace of the system. The minimum or maximum eigenvalues we denoted by lambda underbar, and lambda upper bar. These gives us the times I gives the upper limit and lower limit of this mass matrix. And similar to that, the inverse could be also found by the inverse of the lower eigenvalue and upper eigenvalue of the system. This means that usually if we talk about control aspect of a mass matrix, the norm of a mass matrix is always all bounded, regardless of what kind of norm you are using. We usually use the U2 norm or induced norm of matrices, but the norm of the mass matrix is also constrained by its upper and lower bound given in here. We can furthermore go to some adaptive techniques in the control because of this property of the whole dynamic equation. As you see, this dynamic equation that we found, even for very simple manipulator, the elbow manipulator with 2R structure, is usually nonlinear with respect to Q. And it is multivariable. So this is a general multivariable and nonlinear equation when we are considering it with respect to Q, especially the V term. As you saw, we have the Coriolis term and we have the centrifugal term, the squared, the dot-Moore product of the velocity, linear velocity and angular velocity, and it is heavily computationally very intensive. Although this equation is so hard, if we can compare it or reduce it to the cinematic and kinematic parameters of the system, like the length of the parameter, the mass of the links, center of mass, the moment of inertia, something that about the parameters of the system. If we write this, we can see that although this equation is completely nonlinear, we can find a set of parameters for the system like the mass, center of mass, moment of inertia, so forth and so on for each link, that the system can be write in a linear regression form. We call it regression because we would like to use some sort of statistical value for that. We can write it in a linear form. In terms of phi, the parameters of the system, the y can be find a very simple matrix which is quite linear. Of course, it has within this q, y, you have the terms of q and q dot, which might be not linear, but in terms of phi, this is quite linear. And this helps us a lot in terms of adaptive control law that if time limit, we will give in this next chapter. Of course, this is not unique representation. We can have different parameters, set of parameter, changing the parameter state. We have different type of y, but it can be shown that it can be definitely found for any serial manipulator. This y can be found, and also the phi could be a very large number. Let me just talk about it a bit in more detail here. Every mass or every link that we have, it has 10 parameters in general. The first parameter is mass. The second parameter is the center of mass. Center of mass is 3 component, x, y, z, so it would be 4 parameters. And we have also the moment of inertia. The moment of inertia in general is a 3 by 3 matrix, 9 parameter, but since it is symmetric, we have 6 parameters there. So for each link, we have 10 parameters here. So if we have a 6 degree of freedom manipulator, we have 60 parameter space in the phi. But it is the usual and natural form of that. Many of these parameters might not come into the dynamic formulation. For example, if we just move we have planar case. If we have a planar robotic case, the center of mass is not a 3 parameter, it's only 2. And the moment of inertia is not a 6 parameter, it's only 1 parameter. Or if we have only 1 degree of rotation here, then the moment of inertia, all the 6 components does not come into the picture. If we have a general motion in the space, all the 6 parameters come to the picture. But if you have only 1 degree of motion here, then only 1 of the parameters come into the picture. It can be, it has been worked a lot, very, very much in terms of, since it is very useful in the control, we can find a minimum number of parameters that are initiative in that. This can be found by inspection, as I mentioned, to see which parameter shall come to the dynamic formulation and which one shall not. Or it can be also used a very mathematical approach, like singular value decomposition that can be used in here. We have a recent work on dynamic formulation being under review. This gives us very, very effective method to find the minimum number of system parameters. And this equation can be used twofold. First, it can be used for some adaptive control schemes. We will talk about them in next chapter. And also, we call it identification process or calibration process. If we would like to find the real parameters of the robot, the real mass parameters, the real center of mass of the robot, from experiment, we can also again use this linear regression form and some techniques in calibration process, which we cannot cover in this introductory course, but this is also very, very fantastic idea. Optimization and least square method can be used in here to find the parameters, the calibration parameters of the robot. Let me give an example here to see what we mean. We have the dynamic formulation for 2R. A few slides back, I have written the dynamic equation here. As you see, we have a lot of numbers, M1, A1, M2, A1, A2, different parameters coming to picture. And we have a very, very large number of parameters. And as you see, these equations are not linear with respect to Q, with respect to theta. As you see, you have sine of theta here, you have multiplication of theta 1, theta 2 in the equation, and so forth and so on. But by inspection and by just some manipulation, we can find a number of parameters here. As I mentioned here, we have given you only 7 parameters. This equation also holds for when we have friction in the joints. If we don't have friction in the joints, we use only 5 parameters here. But if we have these 2, we have 7 parameters. Consider this parameter as the first parameter, A1 plus 1/3 of A2 as the second parameter times M2. This one as the third parameter, this plus this as the first parameter, the second parameter, this one, and the third parameter comes from here, 1 over M2 from this parameter. This is somehow repeating. And then if you go further, you can see the same parameter can be used in here. The gravity terms shall be have some other parameter. This is the fourth parameter and the fifth parameter. And the rest can be just defined by this 5 parameter. And the viscous parameters are our 6th and 7th parameter. Then we can find the M matrix by this parameter using the Q1s, M1, the G matrices and V matrices here, and then finally the total equation can be written this equation can be written in a linear form, where we have a matrix depending on the theta or theta dot multiplied by the number of parameters. The number of parameters are given in here, as you see in this form. And of course, this is not a unique representation. You can have a different type of representation. This can be done for every single manipulator, regardless of the degrees of freedom that you are being used. But next, this is also very important properties of the matrix formulation. We call it Christoffel matrix. This comes from the name of a scientist who works on the dynamic properties or dynamic matrices. We can show that the V vector, the Coriolis terms and centrifugal terms, can also be represented by a matrix, Christoffel matrix, times Q dot. And we can show that, again, this is not a unique representation, but C is much more beneficial to us than V. Although these two are the same, this matrix representation will give us a very, very important property. We call it skew symmetricity. You can find that the C matrix is skew symmetric by some manipulation that I will show you for any manipulator. And this skew symmetricity will help us in the control problem to remove this from many control stability problem and control design. We will talk about the properties of that in the next chapter, but what is the skew symmetricity problem? Let me give a bit of mathematics here. Of course, it can be shown by regular mathematics, but if we use a Chronicle product, that makes us a lot easier. I don't want to go to very detail of the Chronicle product to you. I just want to give you a number of properties for that. A Chronicle product is when we have two matrices, A n by m, B p by r. We call this, we note it by a Chronicle product by a squared, by a circled cross. This means that we multiply all the element-wise together. So if we have a n by m and p by r, we have np by mr matrix. We have a very large, just every element of that is multiplied by the B matrix, and it would be a block there instead of the one component here. This will, of course, make the manipulation, the size of manipulation large. But if we use the I matrix, we can show that it is the Chronicle product is very usefully used for changing a vector to a matrix form. And you can see that I cross X is not equal to X cross I. It doesn't have the commutative properties because of the this by Y by 1 property. But we can show that I cross X times X, this is a matrix and this is a vector, is equal to X cross I times X. And this will reduce the size of the manipulation very much. This is one of the properties we can use. This can be seen in any algebra book. You can find the proof in here. But what I would like to use is, especially for the V term, we have a partial K with respect to Q, partial A, with, let's say partial A, a matrix with respect to Q, which is a vector form in this case. And if this is multiplied by a B matrix, if we have a partial of A times B that we have in our V calculation, we can simplify this by a Chronicle product here times the derivative of B by a Chronicle product and the partial derivative of A times the B matrix. We use these two relations from Chronicle and then start working on the V product. Now, assuming that you follow me with these two and just accept my claim about these two properties, we can see that now the V matrix was the most sophisticated part of the dynamic equation. It has the m dot value and also a partial value of a quadratic form here. And now we can rewrite that the m dot, we can extract Q here. If we can just use the Chronicle product in here, we can show that this is quite easily can find by this equation that I showed you, that can be very easily find that this is equal to that, noticing that partial Q dot with respect to Q is equal to 0. And we will work with that. Of course, this general mathematic problem is very useful since we don't want to use component-wise or one by one for each manipulator. These properties will hold for all manipulators, not just for this one single manipulator. Now, if we have this, we can easily, as you see, we can easily find the V vector in terms of a matrix form, in terms of a Christoffel matrix. Since this is not unique, I write it C1, the first representation of the Christoffel matrix, can be just simply by these two equations, m dot Q, you find the m dot plus, and we call this one as U, unitary or some special matrix, where U is basically this. Don't consider this, if this is very hard for you to represent, this is very easily 1/2 of U. We can see that this is equal to diagonal Q dot multiplied by a vector, a row vector wise partial M with respect to Q. This is done by hand, and this is a representation for a mathematical representation for this. And this can be seen that this is quite easily found by that. Now, the first Christoffel matrix can be found by m dot, find the derivative, term by term derivative of m with respect to time. This is very easily done. Of course, not the calculation might be a bit burdened, but it can be done usually by hand or by matrix, by symbolic manipulation. And this term is basically Q dot times this partial derivative of m with respect to Q. So for here, we need a time derivatives and partial derivative of that. This comes from the time derivative, and this comes from the partial derivatives. And we can find the C1 in here as the first Christoffel matrix, and the Q dot is just extracted factor out from this matrix and comes out from that. This is not the best, this is the first representation. If we use that, we can show that a second representation is also available there. You don't need to find the m dot. If you have find the Q, we can show that. Of course, this has a proof. We can use the U transpose plus 1/2 U. Note that U transpose is not equal to m dot. M dot is not equal to U transpose, but M dot times Q dot is equal to, this is the key point here, M dot is not equal to U transpose. There are two different matrices, but M dot times Q dot is equal to U transpose Q dot. By proving that, we can write the C2 quite easily, just by simple manipulation of a U. U is again U Q dot times partial derivatives, not very hard. And if you have U, the U transpose you can use in here and find that. C2 is another Christoffel matrix. Again, this is not, the best, but the second one. The third one, of course, we have 400 to 400 different Christoffel matrix, but the third and the most useful and most celebrated Christoffel matrix is if we use M dot plus U transpose minus U. We don't have any 1/2 here. M dot plus U transpose minus U. This is mathematically more, needs more manipulation, but this is much more better in terms of matrix properties. We can show that. The skew symmetricity property remember that we will use that a lot in the next chapter, and even in this chapter, at the end of the chapter, we can show that for all C's, regardless which C you are using, C1, C2, or the C, the most celebrated one, or any different type of Christoffel matrix, Q dot transpose times M dot minus 2C. M dot minus 2C, this is a new matrix. M dot minus 2C times Q dot is equal to 0. This means there's some sort of a skew symmetric matrix. Of course, this is not the definition of skew symmetricity, but this matrix is skew symmetric if this is multiplied by any matrix, not just Q dot, by any matrix, X dot times this, QX dot, X dot transpose times this dot, that is equal to 0. Then this matrix is skew symmetric. And skew symmetric is that you have basically 0 values on the diagonal matrix and then symmetric values on the off-diagonal matrix. But we can show that if this is multiplied by Q dot, not any X, this is always equal to 0, and we will use that a lot. If you use this type of matrix, you can see that this matrix is completely skew symmetric. So M dot minus 2C is equal to is a skew symmetric property matrix, and this multiplied by any vector transposed by any vector is equal to 0. So no matter why, in different books they don't show you the different values of that, but we go with this matrix, and then if we have this matrix, we can see that, we can show that the matrix formulation is always M dot plus CQ dot plus GQ is equal to tau, or is equal to Q, as we defined it by Lagrange formulation. Instead of V, we can use CQ dot. And here we have brought to you the skew symmetricity property of any of these three equations. As you can see, this is C1, M dot minus 2C1 times Q dot. You can see that instead of C1, we can use the first formulation, M dot minus half U, with minus sign. This would be M dot minus 2M plus U hat, and then we have here minus M dot and plus U, and we can see that Q dot U is equal to Q dot M, as we discussed it here, M dot Q U transpose Q dot. This can be easily used by Chronicle Product, and this term is equal to 0. If you use the second one, we have 2U transpose plus U, because we have 2C, 2U transpose plus U. Again, we can multiply Q dot in here, and instead of M dot Q dot, we can use again the same property here, U transpose Q dot in here. And then you can see that we have minus U transpose plus U to U, which 0 is because U is always for any matrix, as we see in the basic in linear algebra. And finally, for this case, this shows it very easily. We don't use Q dot multiplication in here. We can show that this is always a skew symmetric property, because M dot plus U transpose minus U, as you see M dot minus 2C, we have M dot minus M dot plus U transpose minus U. These two goes out, and we have U transpose minus U, and U transpose minus 2U is always a skew symmetric, and we have this skew symmetric property. We have a lot of mathematics written here. We don't want to use all this mathematics. We use the fact that MC skew symmetric. remember that for in the future. And the final property that I would like to mention in here is the passivity property. This is for another part of control, a nonlinear control for the system, passivity-based control for the system. We can show that the amount of energy dissipated by a robot has a negative lower bound. And this is somehow we show that the robot is a naturally passive element. And if we have a number of robots, then we can use passivity for the stability of the motion. This, of course, is advanced nonlinear property, but here we can show it very easily. Q dot times tau with the passivity properties means that Q dot times tau, when we integrate it for any integral, is greater than a negative number. Minus beta is a negative number. But why this comes to the energy dissipation? Q dot times tau, the Q dot and tau is like the torque that is applied to system. When we multiply the torque by angular velocity, we get the power of the system. This has a physical meaning, the power of the system. And when we integrate the power with respect to the its own parameter, with respect to time, then we have the energy of a system in a bound here, and we can show that the energy of the system, the integral, denote the energy produced or dissipated. If it is energy, if it is producing energy, the system might become unstable. When it is dissipating, if it is always dissipating energy, then the system becomes stable. And this, we show that this is always greater than a negative number. So it could be very easily used by that. This is also very easily proved by using the concept of total energy of the system. We call it Hamiltonian, or the total energy of the system, which is the kinetic energy plus potential energy. And then if we take the derivative of that, we reach to something very similar to this. We know that the total energy is always positive. If we take the derivative of that, the derivatives we have here, as you see, the derivative of the first term times the second one, and the derivative of this one times this one, and the derivative of the potential energy. This gives us three terms, mq double dot, or m dot times q, and this is written in the form, in the matrix form that we have the dimension here. And the derivative of the last term is also coming here. The p was easily the gradient of p with respect to q times q dot. And now that we have these two, we have mqq double dot here. And mqq double dot, we saw that mqq double dot is equal to q minus c plus g. We use the tau here, the tau minus c minus g in here. Very good. And then we have m dot here, and then we have a q dot here. Now just use it, factorize together. We have the first term here. We have so many terms in here, but all of them become zero except the first term. And this is because the skew symmetricity property of the matrix C, which is very important, as I mentioned here. We can see q dot is here. Then we have here this one plus this term. We put them together by half. M dot minus 2c. Very good. M dot minus 2c is equal to 0. We know when it is multiplied by q dot. Of course, this q dot is extra. We have only one q dot. This is a mistyping. And then also the last term, we have GQ and partial of P with respect to Q, and that we know that the partial of P with respect to Q is equal to G term. This is also 0. This becomes also 0, and we reduce to only Q dot times T. This can be found by the physical concept of the system, that the power, this is the power of the system. The power of the system is the derivative of the total energy of the system. But mathematically, this comes true by using the Skew symmetricity problem. Now, since Q dot times tau is equal to H dot, this integral is a full integral. We can, instead of using this, we can use H dot here, and then we can integrate it very easily by H minus H dot at time t minus 0, and we can see that this is always positive energy. H is always the positive energy of system. So this is a positive value, and this is also a positive value. This is always greater or equal than minus H0. This means that the energy of the system, when this time is evolved, will reduce from H0. This is always, we have a positive energy. So we have energy that is always greater or equal than minus the initial energy of the system, and this is exactly the passivity property that we have used in here when we use, instead of beta equal to H0. So by this term, we finalize the properties. Again, if I just remind you, we have 4 properties. The first property is what the mass matrix. Mass matrix is positive definite and has lower and upper bound. We have linearly in parameter, the adaptive form or linear regression form. We have skew symmetricity property for Christoffel matrix, and then we have the passivity as you saw in here. If there is any questions, now is the time to ask your questions.
Hi, may I ask a question?
Sure.
In slide 44, I didn't get how m dot q dot is equal to u transpose q dot, but m dot is not equal to u transpose.
You should work it out by hand. You see here, we have these two terms together, m dot times q dot. When we use C like here, someone might comprehend that this is exactly m dot, but this is not m dot. You can check m dot and u transpose. These are two different properties. But when they are multiplied by q dot, they become the same. This should be extra proven, by hand. But notice that usually, what we have used here, as you see, we have m dot times q dot, v, as you see, m dot times q dot, and this term times q dot. This term, we call it u. And this is totally different from m dot. This is totally different from m dot. This term is this, as you see, q dot partial m with respect to q1. And the difference is the size of these two are basically what we are using is, we are using Chronicle delta. If q dot was on the other side, both of them were the same, but these are not the same.
Okay.
If you just multiply this by q dot and then using the m would be partial m with respect to q times q dot, and these two becomes exactly the same. We can prove that by some simple manipulation that this is equal to that, but in many papers, in many works, these two are considered to be the same, which is not true.
And the regressor format of the dynamics is not unique. Is any format that is more interesting for us, like for in control?
The format it is most interesting for us is the format that it has the lower dimensional case. The lower dimension, the lower capacity of calculation that we require. And as you see here, this is the lower format that we have. We have only 7 parameters here, or 5 parameters in these. And there is a lot of work has been done to find this lower dimensional case. I refer you to our one of our recent work we used the dynamic formulation with virtual work approach, very, very effective approach, and then use this, find this the lower dimensional case. This is also used by singular value decomposition. You can find that.
So we know the number of minimum.
We don't know, but we can find, you just go, when you go by experiment, you find many of them are 0. That you know the maximum number. Each link has 10 parameters, the maximum. But reducing it, how many of these numbers are basically using, you can find it by inspection. It is hard, you should have a mechanical insight to find how many parameters are unique. But you can very easily find it by mathematics. You just put the input-output to it, that many parameters becomes 0 or very close to 0 with a threshold to 0. You can see that many number of the parameters are not useful, and then by singular value decomposition, you reduce the 0 values and find the rest of the matrices. There are some approaches to do that. Of course, it has a long way. It is about 25 years that they are working on this parameter. This is well established. You can check the literature into that.
And upper and lower bound property of the mass matrix, is it because of its positive definiteness?
Exactly. Yeah, exactly, because of that. The norm is also used because in many control properties, we have uncertain properties, and then the uncertainty are represented by norms, and then we can use that this norm is bounded and it is not unbounded for the stability approach.
And my last question, can I ask the last
one? Sure.
I understand that for the passivity we have, it's come from the power and energy that it's dissipated in the system, but I don't understand its physical meaning of passivity.
You are not familiar with the nonlinear control based on passivity approach. You should read that in any book, especially in Khalil. There is a chapter on passivity. We have 2 approach for stability analysis in nonlinear control. They are very, very closely related to each other. One of them is Lyapunov, that you are familiar. The second is passivity. The passivity is in somehow very related, as you see, very related to the energy and dissipation of energy. But somehow it might be easy to use passivity. If you have interconnection of some system, suppose that you have 3 different subsystems, and you have proven that all subsystems are stable. The Lyapunov approach doesn't mean that although all the subsystems are stable, you should still find a new Lyapunov function for the whole system to find the stability of the system. And this is the limitation of, or the difficulty of using Lyapunov function. Of course, you know that I am the fan of Lyapunov approach, and I really like the way that Lyapunov has think about the stability of the motion. But this is a limitation. The passivity comes after that. It reduced these limitations. So that if you consider that we have some passive element, we have three passive
I cannot hear you correctly.
components of the system, then we interconnect these three. System becomes passive. Provides you with that if some system, if we have three sub-example and each of them are passive two together, then the whole system becomes passive or becomes stable. So this is a newer version of stability analysis, and this approach will help through that.
Thank you, sir.
Do you have my voice? Everybody, my voice is clear?
Yeah, it was broken for a few moments, okay. But then
Perfect. Okay, let me go through the two very interesting other approach. I add a few slide in. Just notice that to get the new slides, of course, there are some mistyping. I will change that, and also have the dynamic formulation for this. This is the benefit of it. And how we can use it. Now, consider that we have the Christoffel matrix, or we have, as you see here, or we have the V matrix, we have the linear regression, we have the passivity, we have the skew symmetricity. What is the benefit? How we can use it? Dynamic formulation is the most significant part of robotic course, since we can use it for dynamic simulation of the robot. If you have a robot built in hand, you have it in experiment, you don't need to simulate it. But usually we build the system through simulation, using MATLAB, Simulink, or other software toolbox. And we call it forward dynamics and inverse dynamics, exactly like what we have in terms of kinematics and also differential kinematics. In forward dynamics, we say that we give the torque to the system. After once torque will come to the peak problem, all the forces or all the torques that are imposed on the system, we are in a vector space, in the Q space, in the joint space dynamics. So we put this together. We have the forward dynamic. We have this formulation, MCQ dot find before MCQG, very effectively find and very intensively find for the robot. And then if we have this, we can find the output trajectory. We give the torque to the system and see how the robot moves. We give a sinusoid motion, we give a torque to the system, and the robot should have some wavy motion. If we give a directly motion to the system, then you have a jumping motion or something like that. To find the motion of the robot and to find how fast or how slow the robot is moving, we can use it by this term. How do we do it in MATLAB or in Simulink? We use the first component of positive definitive M. As you see, we have this equation, and we would like to find the Q. The Q cannot be found directly because we have a differential equation here. And this is very hard to find an analytical approach to find the Q. We can use a numerical approach. We find the Q double dot here. Q double dot is equal to just the M inverse. And since M is invertible, is positive definite, it's always invertible. We don't worry about that. And we can find this in this equation. We have a second order here. And we can use the Rank-Whittle method that you are familiar with. If you are not familiar, please get familiar with this MATLAB function. Of course, the master students are all familiar with that. Some of our bachelor students might not be very familiar with Rangakuta or ODE approach. We can use the ODE or simple for student. I recommend to use the Simulink approach. We have Q double dot. We integrate it and find the Q dot. Of course, Q double dot is with respect to Q and Q dot, as you see. We've put it into state space. We use the dot as the first number of state. Q itself could be the second order. If it is rhythm, it is 2. If we have a 6 degree of rhythm, it is a 6th vector, 6 by 1 vector. So this will be doubled. We have 2 by n vector comes here. The first one, x dot 1 is equal to x2 q dot, and x dot 2 is q double dot is equal to our dynamic formulation. Then we can give it to MATLAB. There is a very, very important sample problem called van der Pol in MATLAB. You can use the van der Pol equation and use that, or we will give you also some simulation MATLAB code that you can use that, and you can use ODE very simply. You give the torques, what is the input torques and the disturbance torques that are them. You give the initial condition, the robot is where is located in the space, then it will integrate it by 1 by and find that stable. You have a motion for the system. I repeat here again that in forward dynamics, we give the input torque to the system, we give the initial condition to the system, and we use a state space 1 degree differentiation vector here. We give this function to the MATLAB, to the ODE function of the MATLAB, and we get the output trajectory of the system, how the system is working. We call that forward dynamics. And if M, C, and G are given, for the structure and the parameters are given, then you have the motion of the system. If you would like to use the first control practice of yours, of course we give it very detailed in the next chapter. If you would like to go to a specific trajectory, you would like to have let's say a very nice and desired trajectory, you can use a feedback here. This is the forward dynamics that we have already, and then you can get the feedback. You give a trajectory, a desired trajectory. We talk about trajectory planning at the beginning of the next chapter. Then we talk about the controller design. You can use a PID controller, very simple, and tune that for now, and see that you can reach to a desired trajectory to the system. This control will make the mechanical structure to move and to have life. If you build a robot and you at the beginning, the first feedback loop that you put on the robot will move as you wish, and this will help you to understand the way it is working. So the feed-forward dynamic can be used, the forward dynamic can be used for in the feedback loop for motion control. We will talk about that. But we have also inverse dynamic. Inverse dynamic in the definition is that the trajectory is given, and you would like to find the required actuator torque to apply to have this motion becoming possible. And this is very, very useful for the design of the or the selection of the motors, as well as that in the control we call inverse dynamic or computed torque. We are computing the torque required to given a specific trajectory. And here we don't need any ODE or any integration. We can simply use this equation. As you see, we have all the parameters here. If you don't have any disturbance torque, you just put everything in here. You find the torque that is required to do that motion. You just need the Q dot and Q double dot in derivative, as we call it, trajectory, to find the required torque. We use both of these in the future of in the next part of the robotic course that we are having with you. Very good. Now let me move on to some more practical robotic terms and some calibration and dynamics. These are some very important issues, more we can call a special or some technical approach rather than some theoretical approach. This part and these two was somehow theoretical, but here you can see some very, very nice and practical means. Of course, we use the theory much in robotic, but we can feel it. We talk about actuator dynamics. We have about 15 minutes. I can spend some time here. You know that we have different type of actuators used in robot. The robot has been started using pneumatic actuators, then some hydraulic robot. We have both of them in our lab, but they are a hassle. And today, almost all the robot manipulators are using electric motors, electrical actuators. And in terms of electrical actuators, we have different electrical actuators. We have usually permanent magnet DC motor. Of course, I have put here Maxton motors, very, very popular and very expensive motors, Swiss-made, as you see. Many of our robots are used this kind of motors within here. The permanent magnet DC motor, PMDC we call it. A new version of that is brushless DC motors. Ali is here. Ali Kahe, no. Ali is working on the drive of brushless DC motors. And we have induction motor, AC motors as well. DC motors are much simpler in terms of drive. But the permanent magnet one usually have a brush, and these brushes will be wearable, and they have a limited life. But brushless DC motor are almost very, very long-term working. And also we can have AC. Also fault hover. This is another great. Anyways, now that we have these three kind of robot, usually we prefer to use brushless DC motors in small robotic prototypes. But if we have heavier robot with like KUKA or Staupli, then we go to AC induction. I don't want to go through the driver design. This is another power electronic course you might have, but we need to go through the control part of it, and I will somehow say that how this small motor can change the dynamics of a very large robot effectively. Let's go one by one. Now, try with the permanent magnet DC motor. Of course, you can follow this through the literature by the AC induction motor. You know how the DC motor works. And the DC motor, basically we have a magnetic field with a permanent. If we have permanent magnet, we have some S and N, permanent one. If not, we can use some winding or some magnetic field flux like phi. And if we have a current, a line, considering it as this one, if we have a current, a wire with a current in a magnetic field, as you see here, a force will apply to that. And this is the important electromechanical part of a DC motor. It will produce a force by having a magnetic flux and a current to the system. And if we put it in this way, we have a force in here, we have a force in here, it will rotate, it will give a torque to your system. These two forces provide a torque to the system. Of course, we don't use a simple wire, we use a number of wires, and as it moves, it moves, to keep the wires forces in one direction, we have a commutator, commutator, and this commutator basically will switch the angle of these wires to have always the same direction to this. So a DC motor has a number of, let's say, 1,000 or maybe 2,000 wires somehow delicately wind up in the way that we can consider that here. Now, when we call it a permanent magnet, when we have a fixed statement with some permanent magnet, we don't use armature. We might have a rotating rotor, and the rotating rotor, we call it armature. This basically provides us with the current that we have, and we have a commutator to switch the direction of the current when we move in here. And as we saw in here, we have two basic formulation here. The first one is the torque generated by this. For a simple loop current, we have K1 phi times I. The torque generated by one wire is related to the flux and related to the current that is passing through the wire. And we have the Lenz's law that we call the back EMF voltage, that if this is basically we have a voltage and the current coming through this here, have always a negative voltage, we call it back EMF voltage, because of the Lenz's law. This is also related to, this is also electromechanical, you know, as you see here, torque is related to the current, and the voltage, the back EMF voltage, is related to the velocity, angular velocity of the motion. And these two are coupled to each other and produce a DC motor to work with constant speed when you apply a constant voltage to it. So if you apply a constant voltage to it, we have it will start generating torque, start moving around, but the Lenz's law doesn't doesn't let the rotor to accelerate and have very high speed. As the speed goes high, the back EMF reduces like a feedback, and you have balanced velocity, angular velocity of the motor. In a usual DC motor, we have about 3,000 RPM to 5,000 RPM velocity speed in here. And the torque that we can get for a small motor is about 1/10 of Newton meters. It's very, very small. The velocity is usually high, and the torques are usually low. If we have a permanent magnet DC motor, this phi is always permanent as a constant. So these two constants will be multiplied to each other. And if you use SI unit, this is important. very interesting that if you use the standard SI unit, the K1 and K2 becomes equal to each other. We call it a torque constant or velocity constant of the motor. Km, or the motor constant, is the relation between the current and the torque and the velocity and the speed, the velocity and the voltage. Remember, current is related to the torque and velocity is related to the voltage. And we need the torque. You remember, we need the torque to have the motion of the system. Why we need the torque? As you remember in this chapter, we need the torque to have the motion for the robot. This torque is generated by a system. Now, we can have also an electrical model for the motor. We have a resistance, we have induction, and we have the electromotive force. And very simply by voltage and back EMF voltage, we can write that Li div dt Ri plus V is equal to the voltage, or the current, the transfer function for the current is Ls plus R, V minus VB. The VB is basically the back EMF voltage, which is related to the velocity. Now, if we just multiply it by Km and then replace this VB here, we can see that the torque generated by the motor is equal to Km V minus Km omega M. First order, it has basically a transient and exponential transient because of Ls plus R. This is a general model for the system, but we don't use that usually. Usually L to R is very, very small, especially in good motors. Is about 10 to power minus 2 to 10 to power minus 3. So in the bandwidth that we require, we can neglect that, and we can consider that tau m is equal to kmr v minus km omega. And this will provide you with a characteristic equation of a motor. This is very important for the design of the robot. You need to know what motor you would like to acquire. And as you see, this relation provides you a linear relation here. We say that tau, as the velocity goes on, moves on, the torque is reduced, as you see in here. We have a Km, Rv, we have a constant value here, K max, and then to avoid overheating a constant, we never keep the motor to stall, basically, and you usually consider this part of the motor as we goes away. As we increase the velocity, as we increase the voltage, we want to V2 to Vmax, the maximum velocity, that the maximum voltage that we can apply to the motor. Then we can have higher speed. We can be anywhere in here. Of course, negative part is also possible. We have a 4-quadrant value. I'm showing only the positive velocity and torque, but we can have negative torque and velocity, just the direction. And we can move around in here. Basically, these are the red one, as we show here. We clamp the current usually by a clamp limiter in the driver of the motor to avoid overheating of the motor and brake of the motor. And we have like this. And in a typical motor, this has been come from one of our DC motors that is available in our lab. Usually we have a continuous operation and intermittent operation. If you would like the motor to move always directly, you should keep not this part, maybe a bit lower than that. But if there are some intermittents, sometimes you have a very peak, very small velocity you would like to have, you can increase the voltage for, let's say, half a second or something, and then reduce it that way. All this can be provided by the driver of the system that we usually are using by this. Why these are important? These are important for the dynamics. I will show you because we are having the torque with respect to the velocity. We have the torque with respect to Q dot for the system. Somehow that we would like to provide in here. Remember that somehow these are the limitation of the velocities and also the torques that we are using into the system. And usually, as you see, the back EMF will reduce the velocity or has a disturbance effect to the system. We can use a feedback control to work with this system. And the feedback control is usually the driver of the motor that you usually will, when we have good money, we will buy it. Right now, since we don't have enough money, we will build it, and we have usually both working that way. Another important issue in the, we call it servo amplifier, the driver that we all work, giving the voltage and giving the velocity. We don't use a battery to do that. We usually use a driver to control the current or the voltage that is applied to the motor. And usually the servo amplifier also use a PWM principle of operation, the pulse width modulation. You are all familiar with that. All electrical engineers are much better than me know about the pulse width modulation. If we have in a pulse width modulation, we have a duty cycle. We call it a duty cycle. A duty cycle is if it is half, if the duty cycle is 50%, and V max and V min is equal to each other, we have effective zero voltage. Although we are putting plus and minus volt, the effective voltage to the system is equal to zero. But if the duty cycle is greater than 50 degrees, so if we have a larger maximum value, you see here it is less than 50%, the V out is negative. If it becomes more than that, if it is 100%, so we have the total V max coming to the system, a positive voltage to the system, and we can just use this duty cycle and control the duty cycle to find the voltage of the system. We never, almost never use a direct current for control of the motor. We use the PWM and special electronic to that. And usually the PWM frequency should be higher than the sound that we can hear. It is more than 25 hertz. That you don't hear any noise to that. We can have 100 hertz, even 1 kilohertz for PWM frequency. Now, the important thing that I would like to share with you, these are some practical aspects of the system, and maybe this would be these two would be the last part of this session. We can use the motor to work on a torque mode or a current mode or a velocity mode. If you would like to have faster motion, faster velocities, you have a velocity mode, you control the voltage. If you would like what we did in the dynamic, you would like to control the torque of the motor, you have to go to the current mode and control the current of the system. And we usually have also some current limiter for the system to avoid overheating. This is a practical servo amplifier function diagram, of course not the electronics, but the function diagram. Just let me, this is the motor. You see we have usually two feedback from the motor. One of the feedbacks are the velocity. The other one is the current of the motor. The current can be very simply feedback by using a accurate resistance at the current output current of to the motor to find what is the current of the system. We usually can use the current mode or a velocity mode. As I mentioned here, the current mode and velocity mode, you have a switch here in many driver. You can switch to the current mode or coming to the velocity mode, or this could be set by the microcontroller that you have in the system. So basically we have two feedbacks. If we work in the current mode, we have the modulator and the logic, we have the pulse with modulator. We have some current monitor and the limiter usually to limit the voltage. And we have a feedback loop here. As you see, the current feedback comes in here. Also, the tachometer comes in here, depending on which velocity, which switch we have. We have a command signal. If we are in the current mode, the command signal is the torque required. If we are in the velocity mode, the command mode is the velocity that we require to hear. And we have usually a lead lag or a PID controller tuned here for the system to make sure that the system is working quite well. Of course, we can have also when a lead network, a lead lag network here, different kind of velocity controller can be used in here. And if you are in the practice of Ken2C, usually students are quite well familiar with building a driver with PWM2 system. We have usually an inhibit clamp. We can have some inhibition. We can have forward reverse clamp to just make sure that the motor is running in one way, or you can move it back and forth. And also we can get the system status output to check that everything is working. This is a function diagram of servo amplifier, and we usually are very important to use this type of characteristic of the motor in the system. This is also a frequency response of the system, a true frequency response of the system. If you have this feedback working well, even in a current mode, as you see, we have we can see the motor as a torque source up to about, you can see 100 radian per second. In about 10 hertz or so, you can consider that the back EMF is not disturbing you because of the feedback that you are using, and you are almost giving the function is like a one-to-one. You require a torque and you get the torque up to almost 200-300 radian per second for the system. Of course, when the frequency goes up, you have a low pass filter, and you reduce the servo amplifier mode. This will help us when we have this kind of system to use this model for the torque, to consider that we give the torque required and we get the torque required by a simple gain, that the gain can be considered by the torque motor. Anyways, I conclude my talk in here, and hopefully we'll talk about the gearbox and the effect, the very important effect of gearbox and the dynamic of the system next time. Thank you for being with us. The number of students are limited. We are at the end of month of Ramadan, and it seems that early mornings are becoming a bit hard for some students to join us. Thank you very much for being with us. If there is any question, I am happy to answer. No question. Thank you very much, and have a good day. Goodbye. Take care of yourself.